Let's explore inverse functions. I've got two functions up here, f and g. One is my add 2 function, that would be f. G is my subtract 2 function. I want to go ahead and start with the composition of these two functions. Remember, when we do a composition of functions, we apply functions in a particular order using order of operations. So I'm going to apply g first, and remember, g is my subtract 2 rule, and I'm going to follow that up with my outer function f. F is my add 2 rule. So if you think about just, some generic input x, so for example, I just had 5, and I apply g first, which is the add 2 rule, and I get 7. Then to 7, I apply f, and I do my subtract 2 rule. Look where I end up. I end up with really no change, because I added 2 and I subtracted 2. So what we're expecting in this composition is that we end up with no operator in the end. I am going to expect that we just get the original x value, because the add 2 and the subtract 2 should cancel each other out. So let's go ahead and do the composition. So as I do, f composed with g of x, it is f of g of x. We work inside out with those parentheses. G of x is x minus 2. So I go ahead and start with that substitution. So x minus 2. F is my add 2 function. So if I think of f being applied to any generic input, f of that input is my input plus 2. So input plus 2. Well, I'm applying f to x minus 2. So f of x minus 2 is, use my red pen again, my input plus 2. Okay, that's the f rule. But now I'm giving f x minus 2. So x minus 2 goes here. If I take that box away, look what we've got. We've got x minus 2 plus 2. Minus 2 plus 2 is 0. And we end up with x in the end. So by adding 2, after we subtract 2, by applying these two functions together, we end up having really no operator happening to x when we get our original x back. Just like in our example, we got the 5 back. Well, we call these two inverse functions, and they're inverse functions because they undo one another. So inverse functions undo each other. So we can really rename this. We had f of x equal to x plus 2. We called the other function g, but let's call it f inverse. So by putting that superscript -1, we can use the language that goes along with what it does. So I read this f inverse of x. Let's look at another example, and I want you to start thinking through how to come up with an inverse function. Notice for these, f added 2, so f inverse undid that by subtracting 2. If we do another pair, so take this away, so if we did another pair, and we had, let's have capital G of x. Capital G of x is 4 times x. If I want to come up with its inverse, the opposite of multiplying by 4 would be dividing by 4. So I would expect that g inverse of x would be not multiplying but dividing by 4. And I'll write that as the fraction x divided by 4. If we want to check that, we do the composition to make sure that these two operators undo each other. So g composed with g inverse of x, or you could do, they will both work, g inverse composed with g of x. I'm just going to do one of them. So let's go ahead and we'll do the second one, g inverse composed with g of x. So this is g inverse of g of x. And we work inside out. So we start with our innermost function, which is 4x. So I plug that in. So we have g inverse of 4x. Now I apply g to it. If I write this g out a little more generically, it's whatever the input is divided by 4. So I'm going to take my input and I divide by 4. That's what G inverse does. Our input, though, is a 4x. We can cancel the 4's out, and we get just the x back. So the multiply by 4 was undone by the division by 4. If we do another example, so let's look at, we'll do, I don't know, maybe capital F. And let's combine them. Let's do 2x plus 1. So we know that we're expecting in our inverse function, so I'm going to actually do it algebraically here in a second, but I know that our inverse function needs to include operations that undo the original operations. I have a plus 1, so I know it needs to include a minus 1. And I also have a multiply by 2, so I know that I need to include a divide by 2. When I do an inverse operation, I want to make sure that I'm undoing my my operators in the reverse order. But we can actually let algebra do the work for us. So we're going to find F inverse algebraically. So we're going to find F inverse algebraically. So we know we're going to see these two operators, but we'll let the algebra take care of the work. So I know that f of x is 2x plus 1. Oops, f of, here, let me just start over again. F of x is 2x plus 1. Instead of calling it f of x while I do the algebra, I'm going to call it a y. So y is equal to 2x plus 1. And I'm going to go ahead and isolate my x. So as I'm isolating the x, so I'm going to isolate x. As I'm isolating my x, I really end up undoing everything that happened to the x. So to isolate the x, I subtract the 1 from both sides. Y minus 1 is equal to 2x. There's that minus 1, right? I got it. And then I need to divide both sides by 2 to get x by itself. So I divide 2x by 2, and I divide the entire left side by 2 as well. So we end up with y minus 1 in the numerator, all divided by 2, is equal to x. I almost have my inverse function. Remember, though, we were looking for f inverse of x. We want to use x as those generic inputs. That gives me one additional step. I need to do an xy swap. So in order to do my xy swap, I'm going to take my y value and my x value and change these. In my inverse function, I'm actually replacing inputs and outputs. So inputs and outputs get interchanged, which means I'm going to swap my x and my y. So you've got two general steps here. And once I do my xy swap, I'll be done. So y becomes x, so x minus 1 divided by 2 equals y. So I can call it just a y, but really this undoes f. This is f inverse. So instead of just being general, I'm going to call this f inverse of x.